Okay, so we can open up epoxides under acidic conditions, but we can also open under basic conditions. Now, when I say under basic conditions, I don't mean you always have sodium hydroxide around. I mean you're doing this under conditions that are compatible with strong nucleophiles. Let's make it a capital. Strong nucleophiles. Okay, so let's look at an epoxide. Same epoxide we've seen before with the acidic conditions. Here's our epoxide. Now, under strongly basic conditions, we're not going to be able to protonate our epoxide. So in the previous example, we protonated the epoxide. Let's draw that down here. When we protonated the epoxide, that made this into a strong electrophile. And so it was pretty easy to find a nucleophile that would react with a strong electrophile. I mean, who wouldn't? If you're a nucleophile, show me a strong electrophile. Well, that means this epoxide, this neutral epoxide, is a weak electrophile. And so if we want to react something with a weak electrophile, we need a strong nucleophile. So when I think strong nucleophiles, I think the SN2 reaction, and I think things like sodium azide, sodium cyanide, sodium sulfide. Things like hydroxide can work, but the best ones are things like azides and cyanides. So if we take these and mix these together, what happens is this strong nucleophile will react with our weak electrophile. Now, the reason this is a weak electrophile is the reason it's electrophilic at all is it has all this ring strain. So this thing does want to react because it's going to release all that ring strain. So when our nucleophile attacks, instead of attacking, I forgot my positive charge down there, when this nucleophile attacks, it is going to attack not at the more highly substituted side of the epoxide, but at the less highly substituted side. Remember, this is a strong nucleophile, and strong nucleophiles are sensitive to steric hindrance. So we're going to attack at the less highly substituted carbon. And when we attack, that carbon already has a full octet, so we need to break an old bond, and that old bond is going to be the CO bond of the epoxide. Now, in this case, the stereochemistry that doesn't change is the more highly substituted carbon. That methyl group is still going to be back, and the oxygen is going to be up. And in what form is the oxygen going to be? Well, it's going to have a negative charge because we just broke a bond and made a new lone pair on that oxygen. The stereocenter on the left, however, will get inverted. The azide is going to come in from the opposite face as this CO bond, and that means the hydrogen is going to get pushed up, and the azide will be down. Now, our reaction is not complete. Normally, these reactions, you probably have some water or maybe methanol, some kind of alcohol around. So, and at the end, we have this negatively charged structure. We want our products to be neutral. So what we'll use is our water or our alcohol. In this case, I'm showing methanol. Will act as our proton source to neutralize our O-. Most of our neutralizations so far have been having an oxygen plus, so we deprotonated some oxygen to make it neutral. Here in this case, we have an O-, so we have to protonate it to make it neutral. And so that's our product. We've opened up an epoxide under basic conditions, which means conditions that are compatible with strong nucleophiles. And these strong nucleophiles are typically our classic SN2 type nucleophiles. And if you notice, we still get an anti-addition. The oxygen of the epoxide and the azide are anti to one another. So it's still an overall anti-process. But the regiochemistry has changed. In this case, the nucleophile attacked the less highly substituted carbon. Instead of over here, we had the nucleophile attack the more highly substituted carbon. So we flop which ends of the molecule react, but it's still the same idea, and it still gives us anti-addition.